Model development is shifting from uniform scaling to hardware-specific architectural branching. The engineering focus is now on internal optimization, tailoring the network to match the exact physical limits of the underlying compute. Google DeepMind's Gemma 4 family spans an enormous spectrum of scale. The lineup runs from the 2.3 billion parameter edge models designed for mobile devices all the way up to a 31 billion parameter dense model built for high-end workstations. Instead of using a one-size-fits-all approach, DeepMind engineered entirely distinct neural architectures for each size variant. The goal is to maximize the intelligence extracted per parameter by tailoring the network to the specific hardware it will run on. This release operates under an Apache 2.0 license. Previous iterations came with strict usage conditions, particularly regarding the creation of derivative works. The Apache 2.0 license removes these legal restrictions, allowing developers to modify, deploy, and commercialize the models without friction. To understand how these models function on their respective hardware, we need to examine three specific engineering solutions: the memory optimizations in the edge models, the mixture of experts routing for workstations, and the hybrid attention engine driving the 256,000 token context window. Gemma 4 is an architectural pivot. By tailoring these network topologies to bypass physical memory bottlenecks, DeepMind is targeting the execution of local workflows that were previously restricted to cloud-based servers. Deploying large language models on edge devices like mobile phones or a Raspberry Pi presents severe constraints. These devices have tight thermal limits, low processing power, and, most critically, minimal available video RAM. In traditional dense models, massive global embedding tables occupy a significant portion of active memory space. As data enters the network, pushing it through this singular block creates a severe bottleneck on hardware with low memory bandwidth. For the E2B and E4B models, DeepMind solved this by fracturing that global table into per-layer embeddings. Instead of relying on a single large lookup sequence before the decoding layers, the architecture assigns a small, localized embedding table directly to every individual decoder layer. These tables are used for rapid, isolated lookups. This creates a large discrepancy between the model's total footprint and its active compute load. The E2B model technically holds 5.1 billion parameters in total memory, but because only a small subset is active during any single operation, it runs with the efficiency of a 2.3 billion parameter model. This parameter efficiency frees up enough operational overhead to support a 128,000 token context window directly on edge hardware. Additionally, the conserved memory provides the exact space needed to run a native 300 million parameter audio encoder locally. This enables complex physical applications, like processing real-time speech translation across multiple languages entirely offline without a network connection. Decentralizing parameter lookups through per-layer embeddings eliminates the primary memory choke point. This structural shift is required to achieve high-level multimodal processing on IoT devices without exceeding the inference latency requirements of a real-time system. High-end workstations and consumer GPUs operate with different constraints than mobile devices, prioritizing deep reasoning capabilities. Running a massive 31 billion parameter dense model requires computing every single parameter for every token generated. This creates a high barrier for local inference speed and sustained VRAM usage. To address this, DeepMind engineered the 26B A4B model. This uses a mixture of experts architecture explicitly designed to maximize inference speed. The network contains 128 total experts and one shared expert. When a token enters the central routing hub, the network evaluates the data and directs it to the most relevant pathways, activating only 8 specialized expert nodes per forward pass. This chart shows that while the model stores a full 25.2 billion total parameters, it only actively computes 3.8 billion parameters during generation. By storing vast amounts of data in dormant parameters, the model can process highly complex biological data or advanced coding queries by routing them strictly to the subnetworks specialized in those exact domains. In benchmark testing on mathematical reasoning like AIME 2026 and multilingual understanding in MMLU, the 26B mixture of experts model competes directly with models up to 10 times its active parameter size. This architecture successfully decouples reasoning capacity from inference latency. Developers can execute logic on par with a 31 billion parameter dense model, while maintaining the inference throughput typically associated with a much smaller 4 billion parameter model. Scaling up to a 256,000 token context window presents a distinct mathematical problem. Standard self-attention mechanisms scale quadratically, meaning a massive context window will quickly exhaust available memory during computation. DeepMind bypassed the scaling curve by implementing a mechanism known as hybrid attention. This system operates in two parts. First, a 1024 token sliding window moves sequentially across the data, processing local context in small, manageable chunks without attempting to read the entire document at once. Second, the network interleaves periodic global attention passes. This ensures the model maintains deep contextual awareness of the full sequence, culminating in a final layer that possesses a complete global understanding of the document. Executing those global attention passes over 250,000 tokens requires aggressive secondary memory optimizations to prevent VRAM crashes. The architecture applies proportional rope to manage positional data and unifies the keys and values in the global layers to compress the memory footprint. The final optimization is the shared KV cache mechanism. When the first neural layer computes its short-term memory block, subsequent layers do not compute their own memory. Instead, they snap back to access the exact same block. Traditional models waste compute cycles and VRAM by forcing every single layer to recalculate fresh memory states from scratch. Sharing this cache eliminates that redundancy. DeepMind paired these structural efficiencies with rigorous data preparation, heavily curating the training pipeline and applying strict CSAM filtering. Feeding the model highly curated data acts as a force multiplier for the shared KV cache. Removing noise and low-quality information ensures that the long context memory remains precise and highly relevant. Processing a 250,000 token context window is not achieved by simply adding more hardware VRAM. It requires surgically eliminating redundant memory calculations across the entire attention stack. Previous generations of vision models destructively compressed images into fixed square bounding boxes, forcing spatial data to fit into preconceived shapes. But Gemma 4 natively processes variable aspect ratios and resolutions, analyzing the image exactly as it exists in the real world. To manage the compute cost of this data, the model introduces a configurable token budget. This grants developers manual control over exactly how many tokens are assigned to represent an image. This diagram shows the direct trade-off. A low budget of 70 tokens is highly efficient for basic tasks like broad classification. But for dense visual details like document OCR, developers can allocate up to 1,120 tokens to preserve fine-grained structures. By exposing the token budget, DeepMind allows engineers to dynamically trade spatial resolution for inference speed, dialing in the compute requirements based on the exact needs of the task. The Gemma 4 strategy relies on pairing highly curated training data with hardware-targeted structural fragmentation. The Apache 2.0 license legally enables these specialized models to be deployed directly into commercial production pipelines. The model includes native support for structured tool use and function calling across all sizes. Function calling enables the model to interact directly with external environments. It can execute code, navigate application interfaces, and trigger APIs to complete multi-step tasks. Running these models completely offline provides critical security and privacy benefits, while decoupling enterprise workflows from cloud rate limits and external subscription fees. Gemma 4 provides the foundational architecture for a local AI operating system, engineered to scale efficiently from an offline Raspberry Pi up to a multi-GPU research server.